Hello and welcome. My name is Noah Deere, and today we are doing Lesson 20, Triple Integrals in Cylindrical and Spherical Coordinates for the Vector Calculus 1, Math 254 at Portland Community College. This is our last lesson in the sequence. Today we are going to go over triple integrals in cylindrical coordinates, so we'll look at how to formulate that and see that it's essentially just what we were doing with polar coordinates for triple integrals in the last lesson. We'll then look at triple integrals in spherical coordinates, formulate how to do that, why we do some of the things that we do in that formula, and then go ahead and practice using it. And finally we'll do an example of an application of triple integrals, of finding the centroid of a solid, a three-dimensional solid, as before we'd only done that for the two-dimensional laminas. So now we can do it in three dimensions. Let's go ahead and jump right in here. Section 20.1, Triple Integrals in Cylindrical Coordinates. So this is really a simple extension of polar coordinates when we're doing triple integrals in cylindrical coordinates. Remember, we can find a double integral in polar coordinates using the double integral over a domain D of f of x comma y dA equals the integral from theta naught to theta final of the integral of the lower radius as a function of theta to the upper radius as a function of theta of f of r cosine of theta comma r sine of theta r dr d theta. Now in cylindrical coordinates we have x equals r cosine of theta and y equals r sine of theta and z equals z, which is the same as polar coordinates except for now we have a z component. So the z component retains its own value. Thus, given a triple integral in rectangular coordinates, we can do the following. We have the triple integral over some domain E of f of x comma y comma z d capital V. Well, if I just do the z direction, then this equals the double integral over a domain D of the integral from a lower z bound as a function of x and y to an upper z bound as a function of x and y of f of x comma y comma z dz d capital A. So here we just are still in rectangular coordinates, just simply doing the z direction first, and then the domain that we're doing this over in the D is a domain in x and y. Write that down. So then we can take that domain in x and y and do polar coordinates. So this equals the integral from theta naught to theta final of the integral from a lower radius as a function of theta to an upper radius as a function of theta of the integral from a lower z bound, but now we're going to do it as a function of r cosine theta r sine of theta to an upper z bound as a function of r cosine theta r sine of theta. And then our function that we are taking the integral of, we now have in terms of r and theta, so f of r cosine theta, r sine of theta, comma z, all times r dz dr d theta. And so it's that simple for us to set this up. And we really kind of did this in the last lesson, so we're just going to do some more practice of it now. Essentially, we were able to evaluate a triple integral in cylindrical coordinates by converting the x and y variables to polar coordinates, just as we did with double integrals. Let's put this to practice. Example 20.1.1, evaluate the triple integral over a domain E of x cubed plus xy squared d capital V, where E is the solid in the first octant that lies beneath the paraboloid z equals 1 plus x squared plus y squared, and within the cylinder x squared plus y squared equals 2. Okay, so let's go through our bounds here. With this cylinder x squared plus y squared equals 2, we are going to have that our radius squared equals 2, so our radius is going to be between 0 and the square root of 2. We see that in this shape we're going all the way around. It's symmetrical, so theta doesn't have any bounds other than its natural 0 to 2 theta, or to 2 pi rather. And then our z values are going between the xy plane and z equals 1 plus x squared and plus y squared, so that's giving that our z values are between 0 and 1 plus r squared when we put that into polar form. So we can set up our triple integral now. Of x cubed plus xy squared dv that this is going to equal the integral from 0 to 2 pi in the theta direction, from 0 to the square root of 2 in the r direction, and then the integral from 0 to 1 plus r squared in the z direction. Then we're going to have r cubed cosine cubed of theta plus r cosine of theta times r squared sine squared of theta times r dz dr d theta. Right, and that r is from our polar form. And so then this equals the integral. I'm going to do a couple of things rearranging before I start integrating. I'm going to do the integral from 0 to 2 pi, keep that the same, the integral from 0 to the square root of 2, the integral from 0 to 1 plus r squared. And I'm going to multiply the r in. I'm also going to note that cosine cubed theta equals cosine of theta times 1 minus sine squared of theta. This 1 minus sine squared of theta is cosine squared of theta. So this equals cosine of theta minus cosine of theta sine squared of theta. That's going to allow us to do a little bit of a combination here. So this is r to the 4th times cosine of theta minus r to the 4th cosine of theta sine squared of theta. That's all from that cosine cubed and us taking the r to the 4th from the r cubed and the r and distributing it across these two. And then we have plus r to the 3rd and then 4th of cosine of theta sine squared of theta. Move this, I suppose. And then we have dz dr d theta. But this is nice because now these cancel. So I get that this equals the integral from 0 to 2 pi, the integral from 0 to the square root of 2, and the integral from 0 to 1 plus r squared of r to the 4th cosine of theta dz dr d theta. And that's not so bad. So here we get this equals 0 to 2 pi, the integral from 0 to the square root of 2, and then we get 1 plus r squared times r to the 4th is r to the 4th plus r to the 6th cosine of theta dr d theta. And so that's just by me taking the antiderivative with respect to z. Show this. There's kind of an in-between step that I'm doing in my head. Which is great if you're following along, and no big deal if you need to see this here also. It's cosine of theta times z evaluated from 0 to 1 plus r squared dr d theta. So when I plug in the 1 plus r squared for z, that multiplies by the r to give us the r to the 4th plus r to the 6th. Now, I'm going to break this up because the r's and the thetas are completely separate. The bounds don't have any r's or thetas in them. So I can rewrite this as the integral from 0 to 2 pi of cosine of theta d theta times the integral from 0 to the square root of 2 of r to the 4th plus r to the 6th dr. So here we get sine of theta evaluated from 0 to 2 pi times 1/5 r to the 5th plus 1/6 r to the 6th, evaluated from 0 to the square root of 2. And this all equals 0. And that's because sine of 2 pi is 0, sine of 0 is 0, and I don't care what the rest of this is because 0 times anything is 0. So keep in mind how this works is that this is really a hypervolume. This triple integral, the bounds are this volume. So we're integrating over this volume, and due to its symmetry somehow and this function, the outputs in the fourth dimension given by x cubed plus xy squared, that somehow there is positive and negative hypervolume that cancels each other out in this problem in order to give us a hypervolume of 0 for this region, or this four-dimensional region where the w values are given by x cubed plus xy squared, and then our z, x, and y are given by the bounds that we have here in our picture. Okay, so that's our first example. Let's give you an exercise 20.1.1. Use a triple integral to find the volume of the solid capital E, which is bounded above by the sphere x squared plus y squared plus z squared equals 4, and below by the paraboloid 4z equals 4 minus x squared minus y squared. If I take a look at the GeoGebra, there we go. Yep, that's the right one. So we are looking for the volume underneath this sphere here, and above, so we just got that, below by this paraboloid that we see in blue here, and above by the sphere in green. The sphere of radius 2 and the paraboloid with vertex 1 and hitting the xy plane on the circle r equals 2. Alright, go ahead, pause the video, and then I will work through the solution with you here in just a few moments once you've had a chance to try this out yourself. And we're back. So if we have bounded above by the sphere x squared plus y squared plus z squared equals 4, we can write that as z upper bound equals the square root of 4 minus x squared minus y squared, which equals the square root of 4 minus r squared. And then our lower bound is the paraboloid 4z equals 4 minus x squared minus y squared, so that lower bound for z equals 1 minus 1/4 x squared minus 1/4 y squared, which equals 1 minus 1/4 r squared. If we look for the intersection of these, assuming that we couldn't see the graph, so we need to find r by hand as opposed to visually, then we can set these two z bounds equal to each other. 1 minus 1/4 r squared equals the square root of 4 minus r squared. And then I squared both sides to get 1 minus 1/2 r squared plus 1/16 r to the 4th equals 4 minus r squared. I set this equal to 0 to get 1/16 r to the 4th plus 1/2 r squared minus 3 equals 0. Then I multiplied both sides by 16 to get r to the 4th plus 8r squared minus 48 equals 0. This factors as r squared minus 4 times r squared plus 12 equals 0. These only have the solution of r equals 2, so that must be the intersection. So our r values must go from 0 to 2. I did go ahead and draw this domain down here, although it's pretty simple that it's just the circle of radius 2. So we get that our volume equals the integral from 0 to 2 pi in the theta direction, the integral from 0 to 2 in the r direction, the integral from 1 minus 1/4 r squared to the square root of 4 minus r squared in the z direction of r dz dr d theta, the r coming from the fact that we have our polar form. And this really has a 1 inside there because we're just looking for the volume of this solid. We don't have, the fourth dimension is just a height of 1, so that volume equals the hypervolume. So we go ahead and take that this equals 2 pi times the integral from 0 to 2 of r times z evaluated from 1 minus 1/4 r squared to the square root of 4 minus r squared dr. What I did is I recognized that there was no thetas in this, so I did the integral from 0 to 2 pi d theta equals 2 pi out front. And then the integral with respect to z is going to put a z inside the integration, evaluated from the z bounds. The r is still inside there, and I haven't taken the integral with respect to r yet. This then equals 2 pi times the integral of 0 to 2 of r times the square root of 4 minus r squared minus r plus 1/4 r cubed dr. I broke this up so that I took the integral of the last two terms, so this equals 2 pi times bracket the integral from 0 to 2 of r square root of 4 minus r squared dr plus parentheses negative 1/2 r squared plus 1/16 r to the 4th, close parentheses, evaluated from 0 to 2, close that bracket so that the 2 pi is going to be multiplied by everything. Then I'm going to let u equal 4 minus r squared and du equal negative 2r dr for the remaining integral that we have inside here. This then equals 2 pi times bracket the integral from 4 to 0 of negative 1/2 u to the 1/2 du plus negative 2 plus 1, close parentheses, close bracket. The bounds on the integral got switched from 0 to 2 to 4 and 0 from plugging in 0 and 2 for r in my definition for u equaling 4 minus r squared. The negative 2 plus 1 on the outside, that came from evaluating negative 1/2 r squared plus 1/16 r to the 4th from 0 to 2. Our volume now equals 2 pi times bracket negative 1/3 u to the 3/2 evaluated from 4 to 0 minus 1. And this equals 2 pi times bracket 0 plus 8/3 minus 1, which equals 10 pi over 3. And so that is the volume of this object, bounded above by the sphere of radius 2 and below by the paraboloid z equals 1 minus 1/4 x squared minus 1/4 y squared. Alright, hopefully you followed that pretty well. Let's move on to the next section. We're going to spend a little bit more time here. Section 20.2, triple integrals in spherical coordinates. So in order to set up a triple integral in spherical coordinates with bounds in rho, theta, and phi, remember our spherical coordinates are given by rho, theta, and phi. And we can actually see in figure 20.2.1 again how that all works. Our theta is just like our theta in cylindrical coordinates. It's measured in the xy plane as the angle off of the x-axis towards the y-axis. That is off the x-axis in the counterclockwise direction if we were looking straight down at the xy plane. My phi value is the angle from the z-axis off the positive z-axis downwards towards the xy plane in whatever direction the theta value dictates. And then our rho value is the distance from the origin in all three dimensions together. So if we have bounds in rho, theta, and phi, we need to slice the volume E into spherical wedges. So here we see again in figure 20.2.1 a little wedge in spherical coordinates. So we've cut the wedge even to have two different rho values, a lower rho value of rho sub I and an upper rho value of rho sub I plus 1, and the difference between those being delta rho. And then we have a delta phi. Keep in mind our entire volume E, is going to be some object in 3 space, and we're just looking at cutting a small section. This is really just E sub I comma j comma k, not the entire region whose volume we're looking at. So this subsection of our volume E has a delta rho, like width almost, and then we have cut it in the phi direction from some lower phi value, phi sub k minus 1, to an upper phi value of phi sub k. And then we have it cut in the theta direction as well from a lower theta value of, doesn't actually have a label here, but we'll go with theta sub j, and then an upper theta value of theta sub j plus 1. And this object is nearly rectangular, with a width of delta rho, and then we have this length here in the phi direction, but because we're a distance of rho sub I away from the origin, we have to multiply that by delta phi in order to get the arc length on this inner edge. So this inner edge has a length of rho sub I times delta phi, and then the inner edge that's going in the theta direction, that has been projected down into the xy plane so we can see it a little bit better here. That's going to be the distance r from the origin times delta theta, and r we know equals rho sub I times sine of phi sub k. So our phi sub k is the upper one here, and this is actually the projection of this arc right here down onto the xy plane. So we're doing that upper one, which should be approximately the same length as this one. These are all approximations, again, because here if we're actually looking for a full volume, we're going to be taking the limit as these little wedges volumes go to 0, so we're looking for infinitesimals of them, and then adding up an infinite number of them. And remember that we get that r sub I equals rho sub I times sine of phi sub k because of this little right triangle here, where when I look at the phi sub k as an angle off of the z-axis, its opposite side is the radius from the z-axis out to our arc. There is our r sub I right there. And then this distance from the origin to that arc, that is our phi sub I. So we're using that right triangle to calculate that r sub I equals rho sub I times sine of phi sub k. And so this arc length, which we see in the xy plane out at a distance of r sub I from the origin, which is also the inner edge in the theta direction of our object, it equals r sub I times delta theta, which equals rho sub I times sine of phi sub k times delta theta. Okay, so let's kind of go through the wording on the paper here. In order to find the volume of a single wedge in terms of delta phi, delta theta, and delta phi, let's investigate the figure. We got a typo here, figure 20.2.1. Fix that. So here we see that the region E sub I, comma j, comma k is approximately a rectangular box. While the opposite edges are not exactly the same length, as we take the limit and make these wedges smaller and smaller, the opposite edges limit out to be the same length. Here we see the inner arcs to have dimensions rho sub I times delta phi, and r sub I delta theta equals rho sub I sine of phi sub k times delta theta, and the radial length to be delta rho. And thus we find that the volume of E sub I, comma j, comma k is approximately V of E sub I, comma j, comma k is approximately rho sub I times delta phi times rho sub I sine of phi sub k times delta theta times delta rho, which equals rho sub I squared times sine of phi sub k times delta rho delta theta delta phi. And therefore the hypervolume given by the triple integral over the region E of f of x, comma y, comma z dv can be found in spherical coordinates via this triple integral over the region E of f of x, comma y, comma z d capital V equals the limit as L, M, and N go to infinity of the sum of I equals 1 to L, the sum of j equals 1 to m, the sum of k equals 1 to n of f of rho sub I sine of phi sub k times cosine of theta sub j, comma rho sub I sine of phi sub k sine of theta sub j, comma rho sub I times cosine of phi sub k, close parentheses, times rho sub I squared sine of phi sub k times delta rho delta theta delta phi, which equals the integral from phi sub 0 to phi sub final, and then the integral from theta's lower bound of phi to theta upper bound as a function of phi, and then the integral of rho sub L for lower bound of theta comma phi to my rho upper bound of theta comma phi of f of rho sine of phi cosine of theta comma rho sine of phi sine of theta, comma, rho cosine of phi, times, outside of the function, rho squared sine of phi, d rho d theta d phi. And if I go through this in just a little bit more detail real quick before we go into practicing this, we're plugging in rho sine of phi, cosine of theta, rho sine of phi, sine of theta, rho cosine of phi, because that's our standard spherical coordinates. So this, we're replacing x with its definition in spherical coordinates, y with its formulation in spherical coordinates, and z with its formulation in spherical coordinates. And then essentially the dv equals all of this, and that comes from what we had done above with that work and multiplying those side lengths together in order to get the volume of E sub I comma j comma k. And that's what allows us to get this formulation in spherical coordinates. And so if we want to put this to the test, we're just going to go ahead and apply this formula now. We're not going to go through any of the Riemann stuff. So example 20.2.1, evaluate the triple integral over the region E of x times y times z, d capital V, where E lies between the spheres rho equals 2 and rho equals 4, and above the cone phi equals pi over 3. So let's go ahead and just copy down that formula. Our triple integral over region E of f of x comma y comma z dv, this equals the integral from a lower phi bound to an upper phi bound, and then the integral from a lower theta bound to an upper theta bound, which may be functions of phi, and then we have an integral that gives us a lower rho bound and an upper rho bound that may be functions of theta and phi, of f of rho sine of phi cosine of theta, comma, rho sine of phi sine of theta, comma, rho cosine of phi, times rho squared sine of phi d rho d theta d phi. So we want to apply this formula to this scenario. So our specific integral, the integral over the region E of x, y, z dv, this has a lower phi bound of 0 and an upper phi bound of pi over 3. And that comes from how spherical coordinates work. So we want to keep in mind, it's going to be easiest to just look at this picture here. If we're doing above the cone, phi equals pi over 3. So pi over 3 is here. Here's my z-axis. This is the xy plane. It's not necessarily the x-axis. It's just whatever direction we're looking at. Here is, oh, pi over 3 is, oops. Pi over 3 off the z-axis is here. And so it's, the theta isn't restricted here. We're allowed to go all the way around. So this creates this cone here, and we're looking for above this cone, so that's going from phi is 0 on the z-axis to phi is pi over 3 here. So that's giving us our bounds on phi. And then theta, there are no bounds. We're going all the way around. So 0 to 2 pi in the theta direction. And then our rho is going between 2 and 4. That's given directly in the problem. So now we just plug in our definitions of x, y, and z in spherical coordinates. So we're going to have rho sine of phi cosine of theta for x times rho sine of phi sine of theta for y, and rho cosine of phi for z. And then part of the formula, we now multiply this by rho squared sine of phi, and then d rho, d theta, d phi. Now, a nice thing about this specific triple integral is that the bounds don't have any rhos or phi's or thetas or anything in them, so, and everything inside the integral is multiplication. So I can really separate this out as three separate integrals. So I'm going to take all of the phi stuff and put it with the phi integral. So that's sine of phi again makes a sine squared of phi, a cosine of phi, and a sine of phi again gives us a sine cubed of phi, cosine of phi, d phi, times, now we look at the thetas, 0 to 2 pi of cosine of theta, sine of theta, and that's it. D theta times the integral from 2 to 4 of rho to the, we have 1, 2, 3, 4, 5 rows, d rho. Now, in this middle integral, I'm seeing some symmetries here that are going to make this work out kind of interestingly. If I say, so if I'm just looking at that integral from 0 to 2 pi of cosine of theta, sine of theta, d theta, if u equals sine of theta, so du equals cosine of theta, d theta, then this integral equals, if theta is 0, sine of 0 is 0. If theta is 2 pi, sine of 2 pi is 0. And then we have u du in here, which just equals 0. So this whole thing equals 0 because we're going to end up multiplying by 0. So I'm not even going to worry about doing any of the rest of the integrations because I know the middle integral is 0, and whether the others work out to 0 or some other constant when I multiply by 0, we're still going to get 0. So again, the volume that we're looking at, which we see in this picture here, and I can even pull that up. That's not it. It's the next one on my list here. This one. The volume is definitely not 0. But when I integrate as this is the domain that we're integrating over, and then our fourth dimension in W is given by this symmetrical equation x times y times z, then everything ends up just canceling out nicely, so that there ends up being a W values that are positive and negative over this region that all add up to 0 in their totality. I didn't use the graph down here, but it's there in case you wanted to draw any extra pictures of this. Let's go ahead and look at exercise 20.2.1. This is for you to try. It says evaluate the triple integral over the region E of x squared dv, where E is bounded by the xz plane and the hemispheres y equals the square root of 9 minus x squared minus c squared, and y equals the square root of 16 minus x squared minus c squared. Go ahead and pause the video, work through this on your own, and then come back and I will work through the solution with you in just a few moments. And we're back. So exercise 20.2.1, evaluating the triple integral over the region E of x squared dv, where E is bounded by the xz plane and the hemispheres y equals the square root of 9 minus x squared minus c squared, and y equals the square root of 16 minus x squared minus c squared. So rearranging the hemispheres, y equals the square root of 9 minus x squared minus c squared, that becomes x squared plus y squared plus z squared equals 9. The other hemisphere, y equals the square root of 16 minus x squared minus z squared, gets rearranged as x squared plus y squared plus z squared equals 16. that shows us that we're looking between rho equals 3 and rho equals 4, but with positive y values only. Since we're also bounded by the xz plane, that tells us specifically that these positive y values only are giving us bounds on theta of 0 and pi. Here I have a graph of the xy plane, and looking down we have a row of 2 to a row of 3, radius of 2 to a radius of 3, but with only positive y values, then we don't get to have full circles, we just get the half circles above the x-axis, so our theta is going from 0 to pi. There's no bound on my phi value. These hemispheres are allowed to go as high and low in the z direction as we want. Here I do have the graph in GeoGebra where we can look at that. So here, if we're looking, this is backwards. I totally have this backwards. Let me fix it. Okay, so that was actually not a hard fix at all. I just switched those theta bounds, which I had miscalculated when I graphed this earlier. But here we see in the xy plane, which is cutting off the top, so you guys see here the positive y-axis is in that direction, and so we get these hemispheres above this, and the phi value is allowed to go all the way from the positive z-axis to the negative z-axis, so from 0 to pi, no restriction there, so that we get these two hemispheres. So this looks like a cantaloupe cut in half from the side. Okay, so let's go back to our PDF here. So our triple integral over the region E of x squared dv equals the integral from 0 to pi in the phi direction, the integral from 0 to pi in the theta direction, and the integral from 2 to 3 in the rho direction. Plugging in for x, rho sine of phi cosine of theta, we get rho squared sine squared of phi cosine squared of theta times rho squared sine of phi from the definition of our spherical coordinate integral. And then that's with respect to rho, d theta, d phi. Now again, this can be broken up into three separate integrals because the bounds on our integration are constants and everything inside the integral is just multiplication. So this equals the integral from 0 to pi of sine cubed of theta, sine cubed of phi d phi times the integral from 0 to pi of cosine squared of theta d theta times the integral from 2 to 3 of rho to the fourth d rho. Now I'm going to break up the sine cubed of phi. I did this in one step, but off to the side I can show you what I did. This is sine of phi times 1 minus cosine squared of phi by taking a sine squared out and changing it to 1 minus cosine of squared of phi. So this is then sine of phi minus sine of phi times cosine squared of phi. So our volume, our hypervolume, equals the integral from 0 to pi of sine of phi minus sine of phi times cosine squared of phi d phi times the integral from 0 to pi of 1/2 plus 1/2 cosine of 2 theta d theta. That comes from cosine squared of theta equals 1/2 plus 1/2 cosine of 2 theta using a double angle formula from trig. And then the integral from 2 to 3 of rho to the fourth d rho, that is going to become 1/5 rho to the fifth evaluated from 2 to 3. So this whole thing then equals big parentheses negative cosine of phi evaluated from 0 to pi plus the integral from 1 to -1 of u squared du close parentheses times big parentheses 1/2 theta plus 1/4 sine of 2 theta close those parentheses, evaluate from 0 to pi times 243 minus 32 over 5. And that comes from the antiderivative of sine is negative cosine, and we need to evaluate it on the bounds for phi from 0 to pi. Then the next bit of that we have u equals cosine of phi, and du equals negative sine of phi d phi. So we can substitute those in for the sine of phi cosine squared of phi d phi to get the u squared du. The bounds from 0 to pi in the phi direction, if phi is 0, we get u equals 1. If phi is pi, then cosine of pi is -1 as an upper bound on this. Then that's our first integral in the phi direction, and then we go times parentheses 1/2 theta plus 1/4 sine of 2 theta evaluated from 0 to pi. That's just from doing the antiderivative of 1/2 plus 1/2 cosine of 2 theta. And then here we're evaluating 3 to the 5th minus 2 to the 5th is 243 minus 32 times the 1/5 puts that all over the 5. Okay, so we can start evaluating now. This whole thing equals parentheses 2 plus 1/3 u to the 3rd evaluated from 1 to -1, close parentheses, times parentheses pi over 2 plus 0 minus 0 minus 0, close parentheses, times open parentheses 211 over 5, close those parentheses. And that's just from evaluating cosine of phi from 0 to pi, and then applying the negative gives us the positive 2, and then the antiderivative of u squared is 1/3 u cubed, evaluated from 1 to -1, and then evaluating 1/2 theta plus 1/4 sine of 2 theta from 0 to pi gives us the pi over 2 plus 0 minus 0 minus 0. This then equals 2 minus 1/3, close parentheses, times pi over 2 times 211 over 5, which equals 4/3 times pi over 2 times 211 over 5, which equals 422 pi divided by 15. And that is our final answer. All right, let's go ahead and go down to our last section, last problem for this entire term. We have the applications of triple integrals for section 20.3, example 20.3.1. Find the centroid of the solid that is bounded by the xz plane and the hemispheres y equals the square root of 9 minus x squared minus z squared, and y equals the square root of 16 minus x squared minus z squared, assuming the density is constant. So one thing that's nice about this problem is we're leaning on the work we just did in the previous problem, since the solid that we're talking about is exactly this solid from the previous problem. So we can set up essentially the same bounds for our triple integral without having to go through that again. Let's do some quick review of what it means to be a centroid. The centroid of a three-dimensional object is going to be, let's call it C equals the average x value, the average y value, and the average z value over the entire three-dimensional domain. And the average x value, well, if I do review of this in 2 dimensions, if we had a lamina, so 2D review, then the average x value, supposing we have a constant density, is going to be 1 over the entire area times the double integral over the domain of x dA, and the average y value would be 1 over a double integral over the domain of y dA. So in 3 dimensions, we're just going to extend this up so that x average equals 1 over the volume times the triple integral over the region E x dV. Our average y value is going to be 1 over v times the triple integral over the region E y dV, and the average z value equals 1 over v times the triple integral over the region E of z dV. So we've got some triple integrals to go through here, yes? Fortunately, the regions in all of them are the same as the ones we had before. Remember, we had rho is between 3 and 4, and then we had 0 is less than or equal to theta is less than or equal to pi, and we had 0 is less than or equal to phi is less than or equal to pi. So let's do the volume first. The volume is going to be the triple integral, then from 3 to 4 in the rho direction, 0 to pi in both the phi and theta directions. If we're doing a volume, then our inside is just 1, but then we have times rho squared sine of phi d rho d, oops, I don't know why I'm saying sine here, d rho d theta d phi. So this then equals the integral from 0 to pi d phi times the integral from 0 to pi. Oh, I need to put the sign in there. 0 to pi in the phi direction has the sine of phi as part of it, times the integral from 0 to pi in the theta direction is just d theta, and then the integral from 3 to 4 in the rho direction has a rho squared d rho. So this equals negative cosine of phi evaluated from 0 to pi, and then we have times theta evaluated from 0 to pi, and then we have 1/3 rho cubed evaluated from 3 to 4. So this equals cosine of pi is -1, but negate it to get a 1, minus, and then it's negative, so plus cosine of 0 is 1, times pi minus 0, times 4 to the third is 64, minus 27, all over 3. So this equals 2 pi times, let's see, 64 minus 27, that's 37 over 3. 37 times 2 is 74. So the volume is 74 pi over 3, and 1 over the volume equals 3 over 74 pi. All right. So we then want to do the x average. So x bar is going to equal 3 over 74 pi over our triple integral from 0 to pi in the phi direction, from 0 to pi in the theta direction, from 3 to 4 in the rho direction. But now we have to substitute x is rho sine of phi cosine of theta times rho squared sine of phi. Move this over here. And then we have d rho, d theta, d phi. All right, working through this, we have 3 over 74 pi. And again, we can break this up into 3 separate integrals. This is the integral from 0 to pi in the phi direction. Phi's, we have a sine squared in here. And that's d phi. And then in the theta direction, from 0 to pi of cosine of theta, d theta, times, we have a rho cubed, the integral from 3 to 4 of rho cubed d rho. Sine squared, I'm going to use the double angle formula on 3 over 74 pi times the integral from 0 to pi of 1/2 minus 1/2 cosine of 2 phi d phi, and then times sine of theta evaluated from 0 to pi, and then times 1/4 rho to the 4th from 3 to 4, and this all equals 0. And that's because sine of pi is 0, sine of 0 is 0, so we're going to get a times 0 out of all of this. So we can just stop there and not worry about any more integration. Now and this actually makes sense when we think about the solid that we're looking at. If we're looking at this solid, the average x value is clearly 0 in between these. In fact, we should get that the average z value is also 0. It's the average y value that's going to be interesting here. Oops. So let's do the average z value just to get that 0 before we do the hard work of the average y value. So the average z value, this is 3 over 74 pi times the integral from 0 to pi in the phi direction, from 0 to pi in the theta direction, from 3 to 4 in the rho direction, and if we're doing z in here, that's going to be rho cosine of phi times rho squared sine of phi, d rho, d theta, d phi. So this equals 3 over 74 pi times the integral from 0 to pi. In the phi direction, we have cosine of phi, sine of phi, d phi, times the integral from 0 to pi of d theta. There's no thetas at all in this line above here, so then times the integral from 3 to 4 of rho cubed d rho. So it's this first one in the phi direction where we're getting the symmetry. So if we have u equal sine of phi and du equals cosine of phi d phi, this equals 3 over 74 pi times the integral. If phi is 0, then u is 0. If phi is pi, then sine of pi is 0, so u is 0 again, of u du. I'm not going to worry about doing any of the other integration because we see that that is 0, but I do want to copy it down so that I'm getting everything here, not ignoring anything. So this equals 0, as expected. Okay, now the fun one is going to be our y average equals 3 over 74 pi times the integral from 0 to pi in the phi direction, the integral from 0 to pi in the theta direction, and then the integral from 3 to 4 in the rho direction, and then y is rho sine of phi sine of theta times rho squared sine of phi from the definition of spherical coordinates integration, d rho, d theta, d phi. So this now equals 3 over 74 pi. And then our phi's, we've got a sine squared, phi, which we're going to use a double angle formula on, times the integral from 0 to pi. The only theta that we have is sine of theta. And now we see when we do the antiderivative, we'll get a cosine, and that's not going to zero out with those bounds. And then times the integral from 3 to 4 of rho cubed d rho. 3 over 74 pi times the integral from 0 to pi of 1/2 minus 1/2 cosine of 2 phi d phi times negative cosine of theta evaluated from 0 to pi times 1/4 rho to the 4th evaluated from 3 to 4. And so we get equals 3 over 74 pi times 1/2 phi minus 1/4 sine of 2 phi, all evaluated from 0 to pi, and then times cosine of pi is -1, but negate it to get a +1, then minus a negative makes a plus cosine of 0, which is 1, times 4 to the 4th is, let's see, we got 4 times 4 is 16, times 4 is 64, times 2 is 128, times 2 is 256. I should have that memorized. It's 256 minus 3 to the 4th is 81 over 4. And cool, we got all that in parentheses. And so this equals 3 over 74 pi times pi over 2. I believe everything else is going to zero out. We could have 0 when I plug in pi for the sine of 2 phi, and then I get a 0 when I plug in the zeros. Yep, so just the pi over 2 times 2 times 256 minus 81. That is 176, 175 over 4. So this equals, these 2's cancel, pi's cancel, so I get, let's see, just seeing if there's anything else that's going to cancel nicely here. I don't think so. So just the pi's and the 2's cancel, and we get 3 times 175, 150, and 300 is 450. Over 4 times 74 is 128, 296. So the average y value is 450 over 296. Wait, am I getting a factor of 2? Hold on, something's not right here. Oh, 3 times 75 is definitely not 150. Arithmetic is hard. So we got 300, and then 3 times 75 is 150, 225, so 525. There we go. 525 over 296. So the centroid is 0, 525 over 296, 0. And that's it. That's our final answer for the entire term. You're all done. Thank you guys so much for taking part in this class. It's been a pleasure working through these lectures with you, and have a great break.